put certain weights and make some quasi-homogeneous polynomial or stuff like this, or get some Kähler variety with potential. You got plenty of this not rigorously well-conformed field series, and then should give this. Then it has a model topological twist, and you get cohomology classes on MJ and bar. You get actually forms, closed forms, and they represent some cohomology classes, and you integrate to get these things, and grading comes from renormalization group law. Another origin is homological algebra. You start with a compact Z2 graded category with Calabi structure, which can understand its element of negative cyclic homology, and also to get this thing gives you a theory. You get homology classes of non-compactified modular space of curves, and to extend to the boundary, you need to make an additional choice. Namely, you assume that negative cyclic homology is it's a vector bundle on formal line with U variable, and you trivialize it, this vector bundle, define all fibers with zero fiber, which is Hochschild homology, and trivialization should preserve natural duality pairing. It's correspond to action of given tile group. And as far as I understand, it's now this story is essentially complete. Several groups working on it. It was proposed maybe like 20 years ago, more than 20 years ago, this way. So you get also construction of such gadget. And of course, in this lecture will be Gromov-Witten theory. When you directly see curves, not like in homological algebra, it's you don't see complex curves. You do something like ribbon graphs instead of curves. Yeah, and Gromov-Witten theory can do for real symplectic manifolds, and the field for convenience is because you should consider curves of arbitrary degree will be Novikov field, and that's one theory. And fourth version is algebra geometric version. You start with smooth algebraic variety over some field, maybe not zero characteristic, and you also get Gromov-Witten invariance. So you get 4 different constructions, and none of them is particular case of another. So there's really no universal tool. One can try to think maybe categories universal tool, but the categories should take with a grain of salt. Maybe these categories like categories of perfect complexes of non-algebraic variety, so maybe not enough objects. Some strange things. And actually tell you the example when I don't even know where in any sense category is, but there are some Gromov-Witten invariance, some kind of Gromov-Witten invariance. Category and physics maybe are more fundamental, but this Gromov-Witten invariance is kind of particular realization for Foucault category. In usual symplectic geometry, we know that parameters of symplectic manifolds are finitely many locally. For closed symplectic manifolds, you just deform freely class of the symplectic form in open neighborhood in cohomology. It could be conical. So the moduli stack is a conical domain and fundamental vector space of R. You get only real points, and then complex head get complex C star instead of R. You get complex parameter space. And Gromov-Witten invariants are classes in product of homology class, virtual fundamental class of modular space of stable maps. And from this you can build a homological field theory, because for the things you can get like a situation when there's no stable curves, but you still get stable maps. And all, of course, it's based on pseudo-holomorphic maps. Actually, I want to warn you about something here. We are all got used to notion of stable maps. It was introduced very, very early, and there is no justification from physics. I talked to Nikita Nekrasov like 1 week ago, and we realized we both don't understand it. Yeah, the model space of stable maps is a Hausdorff space, yeah, and compact Hausdorff space. And because compact Hausdorff, you consider universal curve, you got again something compact Hausdorff, and because compact Hausdorff you can introduce some metric. So it means that these curves which you map want to have some metric. Which metric they want to have? Curves could be, they can have hyperbolic metric because curve can have genus 0. The condition is that components of the curve which maps to point have hyperbolic metric. But on other components which maps not to the curve, we can make something like pullback of Keller form. So it should be some funny differential equation. Namely, what you should expect, you should have unique solution of the following equation. Sorry, I don't have really room for improvisation with this such setup. Namely, you want to have a metric, a Keller metric on a curve, singular curve, such that if you add a Ricci curvature to this metric, then you get pullback of Keller form. Okay, it's some strange differential equation which one should explain from physics. It wasn't explained, and the whole story is very, very murky. And in fact, how people really get original mirror symmetry prediction, it's really miracle, yeah, because in sense they didn't know about holomorphic anomaly at that time. So all the things is actually non-holomorphic in parameter space. So it's something like function q and q bar, which are complex conjugate variables. Then they kind of set q bar equal to 0, go outside of realm of actual physics, and get series in q. And yeah, what's going on? They didn't understand it, and we don't understand it up to now. Yeah, so it shouldn't be taken for granted, these stable maps. Okay, yeah, in algebraic geometry, you have algebraic curves instead of pseudo-homomorphic curves. And you see that in algebraic geometry, you have a really more fine invariance for which there's really I cannot identify it with anything in other models. So first of all, what is the class of a curve? Of course, we have, let's say, complex algebra. I already said it's class and second homology with integer coefficients. But in fact, I can see the space of Chow groups of one cycles on algebraic variety. It's some kind of infinite inductive limits of some finite dimensional varieties. You start to move curves. And it has infinitely many components, more components than classes in second homology, because you have like invariance in intermediate Jacobian and so on. Yeah, so so degrees you can count in much more fine way, and there's no mirror symmetry prediction for this. Also, this Gromit class, this element kind of virtual fundamental class, it's not just usual homology class in Betti homology, it's algebraic cycles up to rational equivalence now. Before degrees were up to algebraic equivalence, now it's up to rational equivalence. It's again a very huge infinite rank group, and against its face maxims, and I don't know how it follows from categories or whatever. Yeah, it's something different. And of course, if you reduce to usual homology and have variety of complex numbers, then choose Keller metric, then you identify equations from real symplectic geometries and Gromit invariance and Gromit invariance from algebraic geometry. Yeah, and also I explained that algebraic geometries give something more fine, but in symplectic geometry also you get many things which don't come from complex geometry. A lot of symplectic manifolds not algebraic. The first obvious abstraction is that you don't have Lefschetz decomposition, because in projective varieties you do it. And there are plenty of such symplectic manifolds, but also there are symplectic manifolds that's completely different nature. You take a real four-dimensional hyperbolic manifold. Four-dimensional hyperbolic space divided by discrete co-compact torsion-free subgroup. And got this guy, and then consider bundle with fiber S2, something like progression of some spinor bundle. You get 6-dimensional manifold. And Fein and Panov realized that this guy has natural symplectic structure. Yeah, so you get symplectic manifold, 6-dimensional. Then, I don't know, they're not Calabi-Yau maybe, but, or maybe yes, but they're definitely not from the world of algebraic geometry, and what you can get here, I have absolutely no idea. Yeah, and also, just again, return to algebraic geometry, you see that you get positive characteristic. Okay, there's no real symplectic manifolds at all. You can imagine some variety which you cannot even deform to zero characteristic, some kind of very rigid positive characteristic guys. Yeah, I mentioned that you have this group of cycles huge. And also there's another fundamental problem. Imagine that your variety is in zero characteristic, but defined on some number field, like you add square root of 2, for example. Now you have two embeddings of this field to complex numbers. You take plus square root of 2 minus square root of 2. And then you get two different symplectic manifolds. And this symplectic manifolds, you cannot really identify their Betti homology. There's really no reason for them to be. They have the same rank, but not isomorphic at all. And manifolds could be non-symplectomorphic, and one can imagine a situation in, for example, they have like different homotopy type, different fundamental group. Yeah, there are examples of Serre. He discovered simple examples of some families of abelian varieties or something. If you make different embedding, you get different fundamental group. Yeah. Yeah, I mentioned that category is sometimes very small, and here something very mysterious goes on. You get two different symplectic manifolds, two different Foucault categories which have no reasons to be equivalent, because things are different. But modular space of these categories, which is described by this geometry, the deformation of categories, giving this variation of what the hot structures, are the same after extension of scalars. From categorical point of view, it's something very bizarre going on. Kind of different categories have, after extension of scales, the same modular spaces. What's going on, I don't really understand. Okay, now after this just introduction or lamenting about that many different things, I'll just remind briefly atom theory, which I explained maybe too many times on this conference, but let me ask me to explain again. Okay, just do. Yeah, so the formalism which we use in paper with Ludmil, Tony, and Tony is maximal F bundles. It's encodes only genus 0 part of cohomological field theory. High genus should be some kind of quantized, but I will not talk about high genus at all. Yeah, and when consider genus 0 invariance, it's usually people encode in Frobenius manifold to get some affine space with translation invariant metric, just your vector space with scalar product. And on the space you got geometric function of genus 0 invariance, such as third derivative is a W dBV equation. So the basic thing, you get affine structure, and this affine structure is not really natural if you want look on the things, and so we ignore it. Yeah, so I recall that F bundle is a supermanifold of some field, characteristic 0, but supermanifold in kind of various types of geometry could be analytic, formal, or maybe even algebraic, but it's very rare. It's more like formal or analytic. And with a supervector bundle, on your manifold, supermanifold will lie by formal line with coordinate u, with meromorphic connection such that it has second order pole along u, and u squared du, it will be regular operator without poles, and u times vector field also will be regular operator and get vector field on base. Yeah, so it's purely kind of differential geometric notion, and then we have such a bundle. Then by taking a residue part of this WXI, you get an action of tangent space of the base by commuting operator on fiber of this bundled point u equal to 0. So you get a bunch of commuting operators, and like we call this maximal of bundle. This is kind of like maximal commuting family. Maximal commuting family essentially says that you get a cyclic vector. So you kind of you cannot which identify tangent bundle with the fiber. The choice of only existences we ask of the cyclic vector, not the choice. And this implies that tangent bundles commutative, supercommutative associative unital algebra, and taking residue of u squared du, you get another commuting element. It will be correspond to elements of this algebra and gives you a vector field which is called Euler vector field on the base. And it rescales the product. Yeah, so it captures nicely this genus zero part with scaling behavior. Yeah, also as a kind of, it's a really technical thing. Sometimes it's convenient to work over non-Archimedean field, adding some formal variable. In order to have more points, you can get things given by form power series. It has only one closed point, but if you extend scalars, you can have the whole neighborhood. And also, in context of Gromit invariance, we can. It's convenient to have this formal dummy parameter just to substitute two coordinates in a Frobenius manifold. There's some special care about second homology, the exponential of coordinates, and not second homology, usual coordinates. Yeah, that's really just a trick in order to avoid the equation of convergence over complex numbers, which is still unsolved, and but we believe it's true. And why we have to go to tricks to prove some theorems. Yeah, and then otherwise it will be hypothetical results. Yeah. It's really just technical trick at the moment. It's nothing deep here, and effectively we think the things are convergence over complex numbers, and also in variable u should be not formal but analytic disk. And analytic behavior in U in complex numbers is the same as complex formal bundle or formal disk plus some kind of Stokes data. And Stokes data doesn't really talk at all with the rest. It's kind of like extra parameter, which is kind of which is locally constant, kind of asymptotic. It's some finite collection of some numbers, matrices. That's the difference between analytic and formal version. Yeah, when you do category theory, kind of abstract category theory, you automatically have formal power series in U. You don't have intrinsically any analytic dependence, because this notion of theory is kind of too abstract. So you get formal maximal bundle. Also in parameter space, also you get formal deformation theory, like formal DG manifold. And you not in general you get just without any condition, not Calabi-Yau, not smooth and proper, you get kind of like DG-F bundle, not maximal. The base will be DG manifold, and the fibers will be this bundle will be negative cyclic homology, and a connection will be connection periodic cyclic homology. So it all has clean categorical origin. And to have this F bundle, you want to have smooth modular space, and the natural and also condition of maximality, Hochschild cohomology, have the same size as Hochschild homology, and the natural source of such things is that when your category is Calabi-Yau category, so you can identify Hochschild homology and Hochschild cohomology. And for smoothness, you need the spectral sequence of Hochschild to Durham to degenerate. So negative cyclic homology will be free module. And in my second talk, I will describe this kind of not formal but actual analytic version in context of Landau-Ginzburg models. One can see these things in the whole glory with also with Stokes parameters and so on. And I recall that you have this spectral decomposition. You get F maximal F bundle, or actually F bundle in any sense. And then at any point, you get earlier operator acting on the fiber, and it has some eigenvalues, which are critical values of the potential Landau-Ginzburg model. Yeah, so these things arise universally in category series as well. Yeah, so you get the spectrum for free, and then there is easy fact that you get this eigenvalue. So the Stankin space splits in the direct sum of some subspaces, and then the claim that the base splits in the product of submanifolds correspond to discrete eigenvalues. Each of them again it will be a base of maximal of bundle, if you have this maximal bundle story, and it's not true analytic case because some Stokes parameters of this simplification will disappear, will be lost. But for base it gets the product structure, and also you can divide again as a group, also get product decomposition. And I recall this original blob. You can it's just in symplectic framework. You make symplectic manifold, symplectic submanifold. There is symplectic blob, which carries not canonical symplectic form, but like one parameter family of symplectic forms. You add pullback of symplectic forms, some small multiple of exceptional divisor. And then we make a calculation in a classical limit, and you see some clustering. You get several copies of shifted copies by roots of one of the central blobs, and in the around zero you get eigenvalues for your variety Y. So you see it's naturally split by several groups, and that suggests that this Frobenius, these factors in spectral decomposition will be really F bundles for Y and Z, and which Iritani proves. Okay. Now, what was the idea of this theory of atoms? Now we try to exploit the fact that our variety is simultaneously symplectic and algebraic, and Gromfeld invariants are given by algebraic cycles. Now, I told you that in algebraic geometry you can start with varieties of arbitrary field, any characteristic, but in positive characteristics there are some problems. First, there's at least for application to rationality equations, we need resolution of singularity, which is not yet proven. But another problem is that theory of motives is a bit hypothetical in positive characteristic. Yeah, so it's at least like for proving theorems, it's not useful. But in characteristic zero, everything is fine. You get resolution singularity and get intrinsic theory of motives, which was proposed by André, and namely the claim that there is, if you get a field of characteristic zero, you can have some canonical tensor category over rational numbers, and you get some cohomology theory with values in this category. But it's not some mysterious category. It's a mysterious category, but if you choose embedding of your field to complex numbers, this category will be will map to vector spaces. And so you get fiber functor. It means that and this cohomology theory became just usual Betti homology after this complex embedding. You get different embedding, different realization. Yeah. So it's so if you choose embedding, you get some pro-reductive algebraic group, and if you change embedding, you get some twisted inner form of this group. I said it's this is thing constructed by André, but in fact it's extremely cheap construction. It uses really nothing. It's no knowledge of algebraic geometry is needed. You need only know Lefschetz decomposition for Kähler manifolds, and that's it. I can tell you in words how one can describe this category in plain terms. So if you have variety, we want to think about its cohomology. You have the direct sum of cohomology different degrees. You fix some degree, and then this degree it will be primitive cohomology and copies of primitive cohomology if you multiply by ample class. So it'll be some kind of like a constituents which you can try to think it's primitive cohomology in given degree. Now, if you have product of now you construct choose finitely many varieties. To start with, not all varieties. You just pick some finite collection of varieties. You play with, and for each pair of varieties, you choose finitely many algebraic cycles in their product until there's these correspondences. And now imagine that you do something like Hodge theory. You get these cycles in the products. Then you for cycle in the product you use Q-unit decomposition. You get operators acting from some cohomology of some degree to cohomology of some another degree. Then you choose Lefschetz decomposition. You get some copy of primitive guy to another copy of primitive guy. So it means that for this imaginary summands of cohomology, you get certain maps associated to these guys. Now you start to compose these maps, and you get some quiver. You get some finite quiver. The vertices will be this like primitive parts of individual cohomology group of these varieties, and operators will be all things which can extract from these things. So you get this quiver, and you get path algebra quiver. And then you compose these things, you get a trace which will be rational number by usual Hodge theory and Lefschetz decomposition, because all classes will be rational homology classes. So it means on this algebra we get trace in rational numbers, which can define through any cohomology theory if you want. You take Eliadic cohomology drum, you get not Eliadic numbers, not your field, but actual rational numbers. So you get algebra with a trace, and actually be star algebra. You get so you get some non-negative bilinear form. You mod out by kernel of the form. You get finite dimensional semi-simple algebra with sum of matrix algebras, and it will be kind of like piece of your group algebra of this André group which you see in the story. So it's very, very, very elementary, and doesn't use any standard conjectures at all. And also the things can be set in positive characteristic, but you get like Eliadic number for each element. Says you get rational number independent on L, and after that you get the same story. Now, so it's pretty cheap construction, and then you get this this pro-algebraic pro-reductive group. Tate motives is action of second cohomology of P1. You get apomorphism of GM. This André category, it's something, and fix. You have what I want to say is that you get homomorphism from this Mativi-Gallo group coming from embedding to GM, or you can make it more abstract and categorical level. You get its kernel. And a class of algebraic cycles of any degrees are invariant on the action of this guy. That's the only things which we will use. In principle, again, I want to say that it's this André category. I don't know whether it's really adequate notion for what we are doing with atoms, because it uses Lefschetz decomposition. It doesn't play really any fundamental role in all the story. It's nice to have, but it's more like cohomological degree is important, but left decompositions doesn't really play any role. And you see that about notion of motives, it's just one series of motives, and maybe there is other stuff which behave like algebraic cycles, which you don't know, and maybe they can add it to the game. Yeah, this whole story comes from the observations. There are potentially like maybe Hodge conjecture is wrong, and things which behaves like algebraic cycles on cohomologous theory, but without any apparent reasons. And then it will change the role of the group. Yeah, so it's but this is something which works. Yeah. Now, so using the fact that algebraic cycles are invariant on the action of this bit smaller group, we see that Gromfeld invariance gives you kind of maximal of bundle on which this group acts through some finite dimensional quotient. Yeah, and we define atoms in the following way. We take in this Frobenius manifold fixed locus of this action of this reduced Matveev-Galois group. It will be certain subvariety. Locally, it's just vector subspace. It's submanifold, and for each point of the submanifold, we have even point of the submanifold get certain spectrum. At a generic point, we get some maximal number of eigenvalues. And these eigenvalues, we say it's atoms and local atoms for this variety. And if you get how to relate different varieties, you use isomorphism from Iritani theorems. You identify, you see that this eigenvalue of some variety of blow-up correspond to some eigenvalue for another variety. Yeah, so introduce some equivalence relations on eigenvalues for given variety between all varieties and get something. And we use this theory to get non-rationality results. Yeah, this series also has analog just in pure symplectic geometry. We can have notion of symplectic blow-up, and instead of fixed point of this thing, we consider all even points, we consider generic points what eigenvalues to get some kind of length of the spectrum will be some invariant symplectic manifolds, which is additive for blow-ups, but I have no idea what is it good for. Yeah, in my second lecture, I will say Landau-Gieser model. It will be maybe some geometricalization and get mirror dual. Yeah, okay, and also my second lecture, I will speak about Landau-Gieser model. Then you see that you get actual maps from something to disk, maybe not holomorphic, but at least continuous map to the disk. And then you get cohomology of fibers, and Stokes data in these connections are by Fourier transform. You get some perf zero shifts, constructible shifts which are gamma equal to 0. And this perf zero shifts, because when you have B model, I defined over integers. And so it will be some remarkable lattice for this identification. And many years ago with Lyudmila and Tony, and in parallel with Iritani, we describe explicitly hypothetical lattice compatible with Stokes data in terms of gamma class. And one can have more ambitious conjectures. If you have Landau-Gieser models, then you get this actual critical values, then connect them by this joint path called Gabrielov path to minus infinity in complex case, then should get semi-orthogonal decomposition of Foucault-Seidel category. And Foucault-Seidel category is assumed to be category of perfect complexes, so it means that you should expect semi-orthogonal decomposition coming from the story. Yeah, that's we solidly believe in Fano case, But now, because all this notion is defined without exhibiting the mirror, we kind of analytically continue and make the conjectures it's true always, but without any apparent reasons. It could be wrong, but I think because we should believe the mathematics is nice, and somewhere, so it should be nice to us, and be fine. And so we should get semi-orthogonal decomposition and even germs of Bayesian stability conditions like imitating exponential integrals. So there was something in all the story which bothered me for a while. I explained to you that if you get variety defined of some, let's say, number field and embedded two different ways to complex numbers, you get different symplectic manifolds, and how we identify this picture. And it turns out there's really no trouble. How to formulate, like, for example, if you formulate gamma conjecture for one embedding, will it true for another embedding? In general, if you consider whole homology of symplectic variety, I don't know. It seems logically independent statements for different embeddings. But if you stick to algebraic part, which we use in the definition of atoms, then it's one can see that it's all the same. Namely, so you have variety over any field of characteristic 0 and defined kind of like algebraic part of homology as a morphisms space, is a vector space of morphisms on the unit object, homology of point in under category of motifs, to the motif of X. It's a finite dimensional vector space over Q, it does depend on choice of embedding. And if we choose an embedding, it will be invariant of this our group. Let's, instead of working with all homology, like this kind of like algebraic part of homology, which will be algebraic cycles and what would be algebraic cycles if standard conjecture were true. So you get a smaller class of observables, and you get smaller Frobenius manifold, purely even. There's no odd homology here. And now we move along the whole base of this F bundle and take eigenvalues. So it literally does depend on embedding. And I claim this spectrum, although calculate spectrum on smaller space, coincides with the spectrum on larger space. This argument we also have in paper with Lidmila and Tony. The reason is because this connection is given by kind of algebraic classes, and then projections are linear combination of these algebraic classes. And that's essentially this. So you can do calculation kind of independent on embedding, which is actually very nice from point of view if you want to do some, I don't know, computer algebra experiment. You want to calculate non-future invariance, you want to just say what are homology of your variety. And you try to think it's very unpleasant. You think about Bethe homology, and you have complicated variety. How you calculate Bethe homology? You have like cell decomposition of something. It's unreasonable. You want to calculate de Rham homology, which is more reasonable, but it's again something. Field could be big, and But this algebraic classes, it's some nice kind of space over rational numbers or integers, and one can get total control if you get like finitely many cycles, endomorphisms, calculate traces. It's something which you can do, and then you get the series with rational coefficients, and then you get this whole story intrinsically defined independent on embedding. But what I told you that what goes on when we consider this SOD, whatever, this gamma conjecture should exist beyond these algebraic classes, and here I have really no idea what goes on, how it depends on the fields of definition. And now kind of, that's kind of one kind of new message. It's an optimistic message that it's really no trouble to with embeddings. fields of complex numbers. But now this last part is some extension of theory, something called relative Gromov-Peterson invariance. What we want to in birational geometry to study questions over various non-algebraically closed fields. And non-algebraically closed fields, kind of first example could be some number fields, or it could be fields of rational functions on some varieties. Of course, it could be some even more complicated, but let's do fields of rational functions on some variety of complex numbers, for example, just to keep story easy. So I have as a base field, or which everything defined will be field of rational function on some smooth projective variety, which I called B. It's not the base of F bundle, it's kind of another base. It's maybe S will be a good better name. And if you have a variety of this field of rational function, you can make a model which should be complex smooth projective variety which maps to this base, which could be like curve. And what I claim that what we get a constructible sheaf of maximal F bundles on the base. Namely, what we do is the following. We take some points on the base. It could be critical value, not critical value, doesn't matter. You take some little open neighborhood and take preimage of this little open neighborhood to get a non-compact variety. And you put some Keller form from the original thing, you get a non-compact symplectic variety, and also with almost complex structure, even with complex structure, yeah? Yeah, so we now go to non-compact varieties. And for some non-compact varieties, you have still well-defined quantum product. What is necessary is certain the following property if you choose almost complex structure, that for any compact subset and for any bound on the area, any rational curve passing through the compact subset is contained in another compact subset. Yeah, so it cannot go to the boundary. And in this situation, you get Gromov-Peterson invariance not as functional cohomology, but polylinear functional cohomology. And that's what we need in these F bundles. We don't need function, we get polylinear functionals, like action of certain operand. Yeah, so you get all this story. And here in complete generality, I'm totally lost. You got this F bundle, blah, blah, blah. I cannot see any category around universally which is responsible for the story. In some cases, I can cook maybe not one category, maybe some diagram of categories, but not individual category, diagram of categories in some good situation. But if you just put this condition of that holomorphic disk don't go to the boundary, of course I have some like local Foucault category of compactly supported object, but in this case it will be really nothing because it's in disk, it cannot have anything inside. Yeah, so it's not adequate to be responsible for homology. So the category language literally fails here. And I think in general we have really no idea how to predict algebraically what will be Gromov-Peterson invariance for this non-compact manifolds. Yeah, so it's a big gap in this categorical project. Yes, so it's that I said that none of this series is universal. Yeah, so it's even symplectic geometry produces something which is not covering neither for physics, not from category theory, but by something else. Yeah. Okay. Yeah. So I get this preimage of a small open domain, and it's clearly that all curves which sit here, we have this compactness property because all curves project to a point. Because there should be curves in a small open domain, should be only point-like map. So it will be only vertical curves. Yeah, so what's going on? You have this modular space of vertical stable maps, and it has this virtual fundamental group class in some Borel-Moore homology, and you use this to define this group between invariants. Stellar coefficients, kind of like action of some operand. And then this thing is compatible with restriction. You get a sheaf. So what's going on? So you get operation acting on cohomology of pullback of this little disk. But because it's proper map, it's the same as cohomology of the fiber. It's a direct image of cohomology. It's a constructible sheaf. And then these polylinear operations are compatible with the structure of a sheaf. So you get sheaf of algebra of certain operands. It will be sheaves of self bundles. And blow up formula gives again some tool to analyze things. Now we get eigenvalues, and here it's really interesting thing goes on. You organize eigenvalues in some groups, and how you organize it? Yeah, you need to have some projectors in certain algebra, and these earlier operators, which you construct simultaneously for different pullbacks of different small disk, come from just one object, and it's a really funny construction from just in topology. Suppose you get smooth compact variety which maps to another base B, which is a proper map, like here. You have family of varieties may be degenerate, but total space is smooth. Then what we have we consider fiber product of the total space with itself of the base. Okay, 2 points which project to the same point. It's certain closed subset in a square of your variety. And if you consider homology class and the subset, you can interpret as a kernel of some integral operators, like from homology to itself, and you can compose them in some obvious way. And so you see that if you consider homology of this fiber product, I assume everything is compact, X is compact, B is compact, you consider arbitrary map from compact manifold to compact manifold, consider this fiber product, then homology will be algebra under convolution. It will be some associative algebra, finite dimensional associative algebra. And this operators, this earlier operator, it's some generic point for Frobenius manifold, which you calculate here. It's some element of this algebra. And we took eigenvalues with projections of eigenvalues. You get some idempotent endomorphisms. Suppose in this algebra or complexification, you get some endomorphism. Homology, consider maybe all even homology, it will be Z2 graded algebra. So you get just some finite dimensional algebra, associative algebra, and take any projector in this algebra. What I claim, it gives you a decomposition projector in the sheaf, which is pretty amazing. You have some global object, and you decompose sheaf, and sheaf could be very, very complicated. Could be very complicated singularities, and you simultaneously everywhere make a direct sum decomposition. And the reason is the following. When you make projector of algebra, you can restrict to open subset and interpret elements of some Borel-Moore homology. If the base is not compact, you consider Borel-Moore homology of the same fiber product, it will be again associative algebra. You get homomorphism for guide to any open domain, then it will be projection open domain, and then you get direct sum decomposition. So it's pretty simple construction, but I think it's have a lot of could be very useful, I don't know, in some representations here, because in this case, you can construct some very, very complicated sheaves as direct summands of some things, make a calculation, some pretty, maybe small associative algebra. So that's the story, and then it opens the following possibility. In all those projects eigenvalues, you see you have projectional cohomology, you have decompositional cohomology, so you get some semi-orthogonal decomposition of your categories. And this semi-orthogonal decomposition, you never see phantoms. because they will correspond to non-trivial eigenspaces in cohomology, and so you don't have categories with zero cohomology. But even in this situation, what can happen is the following. You have this algebra, you have some element of this algebra, and you have element of finite-dimensional algebra which has its own spectrum, how it acts on itself. When it acts on itself, it gets some eigenvalues. You choose any of eigenvalues, you get decomposition of the sheaf, you get some subsheaf of direct image of cohomology, but this direct image can have zero R gamma. Yeah, so in principle, it's I expect that by making notion of eigenvalues inside algebra of element, not how it acts on cohomology, you can see more eigenvalues which you can see in usual theory of atoms. It will be some missing eigenvalues which you don't see in our usual theory, and we'll get atoms in semi-orthogonal decomposition of the category. Phantoms, we get, so it's this construction opens way to see phantoms without any stability conditions and so on, Okay, thank you.